Welcome to my Switching, Routing, and Wireless Essentials course. This should be the CCNA version 7 curriculum. This is the second of 3 courses. Welcome. Module 2, Switching Concepts, focuses predominantly on the switching concepts, such as how the switches actually make forwarding decisions. So we're looking at two main things, and that's frame forwarding and switching domains. The switching domains will be a combination of collision and broadcast domains. So let's jump right into our frame forwarding. So frame forwarding is how we actually will forward frames when we receive them or as they leave. So if it's being received, entering, it's going to be ingress. If it's leaving, it's going to be egress. So as it comes into an interface, ingress, leaving an interface, egress. The switch will forward based on the ingress interface, the receiving interface, and then it will look at the destination MAC. So a switch will use the MAC address table to make those forwarding decisions. A switch will never allow traffic to be forwarded out the interface it is received on. So even with a broadcast, let's assume a device plugged into port A is sending a broadcast. The switch is smart enough to realize it was received on port 1, and it will send out the broadcast out all other ports except 1. The MAC address table is stored in what's called Content Addressable Memory, a CAM table. And by recording the source MAC addresses into the table along with the port it's received on, we can build a map. This allows the switch to learn where MAC addresses are coming from. So the interface that the destination is located on as well. That way we can see what's coming in, what's going out, and that table builds, okay, if I need to send out this MAC address, it's on these ports. Again, it will use both source and destination and egress interfaces to map out where MAC addresses are located. So the switches actually use a two-step process. Examine the source address, add the source MAC if it's not in the table, reset the timer back to 5 minutes and if the source is in the table. That way things can age out if they haven't been seen in a while. The second step will forward. It will examine the destination MAC address and forward out appropriately. So if the destination MAC address is in the MAC address table, it will be forwarded out a specific port that is located in the CAM table, or the MAC address table located in the CAM. If a destination MAC address is not in the table, it will flood out all ports except on the port it was received on. Again, a switch will not forward a frame on the port it is received on. So the table is built both incoming and outgoing MAC addresses. There are two types of forwarding methods used when we are talking about switching. So the two main types of switching methods are store and forward and cut through. Store and forward will receive the entire frame. It will verify that the frame is valid and then will forward it out. Cisco switching prefers this method. However, this means that the switch has to receive the entire frame before forwarding it out, which means that's overhead. Cut-through switching will forward the frame immediately after determining the destination MAC address, meaning if there is an error, cut-through switching will forward out the error, where store and forward switching will not, because store and forward will receive the frame, see the error, then discard the frame altogether. So there's pros and cons for each one of them. So store and forward has two primary characteristics: error checking and buffering. The buffering is basically the ingress interface will buffer the frame while it checks the frame check sequence. This also allows the switch to adjust to a potential difference in speed between ingress and egress ports. So again, there's some pros there. The error checking, again, if there is an error, will discard frame. The cut through will basically be a fragment or frag-free method that will check the destination and ensure the frame is at least the appropriate length, 64 bytes or larger, and will forward it out. The concepts of cut-through switching is appropriate for switching needing latency that's under 10 microseconds, meaning real-time like ish type traffic. Anything that has a time-sensitive response is going to be looking more towards the cut-through switching technology. This will not check the frame check sequence number, so it can propagate errors, but again, this may be some speed concerns. However, because we may have different interfaces with different speeds, being able to use cut-through switching, this may lead to bandwidth issues. Basically, if we have a bunch of incoming ports and we're trying to pump it out one specific egress point, that egress point may become overwhelmed. Also, cut-through switching cannot support ports with different speeds going from ingress and egress because, again, that congestion would build up. So they just don't allow it. Next, we have our two primary switching domains, a collision domain and a broadcast domain. So a collision domain is popular when we had hubs, but realistically with switching, we no longer have a collision domain. Essentially, it eliminated collision domains, and it helped reduce congestion. So when there is a full duplex on a link, the collision domains are completely eliminated. Where there's half duplex, there still may be a collision. Again, a collision is where two signals are on the same wire and they hit each other and stop allowing communication. When we were looking at hubs, a hub would receive a frame and would forward it out all ports. The issue with that is it was just constantly sending out data even to ports it didn't need to send it out on. That led to collisions. Switching no longer has those issues. A broadcast domain extends across a layer 2 network. A broadcast will propagate through layer 1 and layer 2. However, a broadcast will not propagate through a layer 3 device. Only a layer 3 device, specifically a router, will break the broadcast domains, also sometimes referred to as a MAC broadcast domain or LAN broadcast domain, together. The layer 3 device will break them into pieces. So when the layer 2 switch will receive the broadcast, it will flood it out all interfaces, except the one it received on. If there is a switching loop, the broadcasts can actually then loop. In a later chapter, we will actually talk about loop prevention. But again, broadcasts that happen too frequently may cause congestion and causes the switches to run in a poor performance. Because again, a switch has a processor and memory, and broadcasts actually then eat that memory up. So to alleviate network congestion, we have a few options. Basically, we end up with faster port speeds. So depending on the type of switch you have, you may have a gigabit, 10 gig, 100 gigabit port speed. The internals of the switch itself, the fast internal switching could also help increase performance. That is where it will use a fast internal bus or shared memory to improve performance. We could also increase the frame buffer size. This will allow for temporary storage while processing large quantities of frames. We could also have a higher port density, meaning this provides as many ports for the devices to be connected to the LAN at a less cost. Though this also provides for more local traffic with less congestion. You have more devices going to a single device, and that single device could use a faster internal switching mechanism to aid in switching internally. Questions, concerns, please reach out. Thank you.